Welcome to the LATHE Soft Jaw video series, brought to you by Haas Automation. Soft jaws offer several benefits not provided by hard jaws. They align the workpiece exactly to the spindle center every time and locate the back face precisely. They are required when holding difficult shapes and any part that must be made accurately. Today, we are joined by Andrew, one of our Haas certified technicians. In this video, we will demonstrate the proper way to cut OD gripping soft jaws and cover soft jaw fundamentals. The first side of this bearing housing has been completed. We will show you our recommended soft jaw cutting methods as we make the jaws to hold the finished first side of this part. Soft jaws will allow us to maintain the best concentricity to the accurate surfaces we've already machined. Before we start cutting, let's go over some soft jaw fundamentals. First, we need to choose whether we'll use aluminum or steel jaws. Aluminum jaws are typically used to grip lightweight or hollow parts where clamp force is low. Steel jaws will be used where clamping forces are higher, and jaw longevity is important. Second, it's important to choose the right-sized jaw. Soft jaws are available in a few different sizes. When choosing a jaw, it is recommended that you hold at least 1/3 of the workpiece length. For a tall part, we can hold the recommended 1/3 length with a taller jaw. And for a smaller part, we can still hold 1/3 of the part with a small jaw. As the jaw height increases and the part moves away from the chuck face, the clamping force on the part naturally decreases. If the clamping pressure is set too high, in an attempt to increase the clamping force, the soft jaws will be distorted, actually decreasing grip force, and the additional leverage from the longer jaws can overload and damage the chuck. Instead, refer to your chuck documentation to find a balance between grip center height and clamping force. Before we mount the jaws, it's a good idea to clean the serrated faces of the soft jaws and master jaws and the T-slots as well. While we are working at the chuck face, it is worth noting that you should never operate the chuck with the cover plate removed in an attempt to gain additional part clearance. This cover protects the internal moving parts from contamination. If contamination occurs, chuck life can be significantly reduced. You can mount your jaws in a variety of positions. But we chose this position in order to conserve our jaw thickness since we plan to reuse these in the future. Never position the jaw T-nuts outside of the edge of the chuck body. When first mounting the jaws, it's a good idea to set them out as far as possible, just as a starting point. Andrew positions the jaws outwards until the T-nuts are near the edge of the chuck body. When attaching the uncut jaws to the chuck, always torque the jaws in place and refer to the chuck documentation for the correct torque value. In our case, Andrew will torque the M12 bolts holding these steel jaws to 80 foot-pounds. Use a smaller torque value for aluminum jaws to avoid distorting the screw seats. It is also extremely important to lubricate the chuck once a day using 2 or 3 pumps of grease per jaw. Use Chucky's grease or an equivalent boundary lubricant with a high percentage of molybdenum disulfide. If you aren't lubricating the chuck every day using this specific type of grease, clamping force can diminish by 50% or more. When machining soft jaws, they must be clamped tightly against some type of object. One of the best ways to keep soft jaws in position for cutting is to use an adjustable boring ring. The boring ring has 3 adjustable dowels that are meant to be inserted into the jaw screw holes. These slide along the slotted ring body during adjustment and lock in place against the ring when the jaws are clamped. This design allows for slight changes in clamping position to be made easily. When the soft jaws are held tight for cutting, the master jaws should be at the middle of their travel. The chuck clamps most efficiently at this middle travel position. This also allows for adequate clearance when loading parts and for variations in workpiece size when the jaws are used later in production. On Andrew's initial ring placement, we see that he is clamped at the very top of travel. Machining the jaws at this high stroke position would make part loading very difficult, since the jaws would only open a fraction larger than the part size. Conversely, if Andrew were to machine the jaws at a low stroke position, the result would be jaws that have very little travel remaining to grip the part past the nominal diameter. In order to clamp in the desired center of stroke, Andrew unclamps the jaws and rotates the boring ring body slightly, counterclockwise, to bring the adjustable dowels inward slightly. The boring ring is now clamped at the center of the stroke. As you look at your setup, visualize the direction you will be clamping in. Always be sure to clamp with the jaws against the boring ring in the same direction that you will hold the workpiece. Also, visualize the amount of force you will be clamping with. During jaw cutting, clamp the jaws with a force as close as possible to your planned part gripping force. As a basic rule, adjustable boring rings can be used up to 100 psi maximum pressure and 900 RPM maximum speed, but don't exceed the manufacturer's specifications. In our case, we will be clamping the part at 130 psi and the jaws at 100 psi. The difference of 30 psi between these two pressures is not enough to cause problems on this particular part. Keep in mind that there are many situations where you will need to clamp your workpiece at a pressure much higher than your boring ring will allow. We will address that scenario in another video in this series. When you are setting the part gripping pressure, remember there should be a balance between holding force and deformation. High jaw force deforms both the jaws and the workpiece. Low jaw force may allow the workpiece to spin inside the jaws during machining. It's a good idea to reference the chart posted on the side of your machine. Remember, spindle speed also affects outside diameter holding force. Centrifugal force pulls the jaws away from the workpiece and reduces gripping force as spindle speeds increase. Set your chuck pressure based on the highest RPM in your program. To demonstrate the loss of gripping force, we will use this electronic gauge, which displays how much force each jaw is exerting against the workpiece. With our chuck pressure set at 250 psi and the chuck stationary, each jaw is pushing with 19.6 kilonewtons of force, or 13,000 pounds of total force. With the chuck spinning at 3,000 RPM, you can see that the clamping force is reduced by more than half. Now that our preparations are complete, we can use the Haas intuitive programming system to set up our jaw boring operation. We start at the ID Turn tab. We'll be using Tool 1 and work offset 54. We leave Z starting point set to 0, so our boring cycle will start at the face of the jaws, where we set our G54 offset. We set inside diameter to 2.2 inches, just clear of where the insert will start cutting. Our part's nominal outside diameter is 3.950, so we set diameter to cut to 3.95 inches. Cutting our bore to 1 inch deep will give us more than 1/3 part length grip. We set the remaining values conservatively based on the insert we're using to cut these steel jaws. When boring, OD gripping soft jaws cut the inside diameter of the jaws to the nominal workpiece diameter. In our case, the blueprint shows a diameter of 3.950, and so we will bore to the size of 3.950 inches. This graphic illustrates what would happen if you did not cut the nominal part diameter. Undersized jaws will grip along 6 edges, whereas oversized jaws will grip only along the center of each jaw. Our program is set to cut at the nominal part diameter. The soft jaws are clamping inwards on the boring ring at 100 psi, which matches the direction and pressure we'll use when cutting the parts. The master jaws are at the center of their stroke. Now we're ready to cut these jaws. Once the jaws have been cut, make a shallow groove at the bottom of the jaws. Any workpiece with sharp edges will now locate correctly against the jaw's back face. Without this groove cut, a sharp-edged part will not locate correctly on the back face. You will likely need to deburr the jaws when the machining is complete. Now that they have been bored, grooved, and deburred, these jaws are ready for use. In some cases, you won't be able to use the adjustable boring ring because the part diameter is so large that the ring itself will block your cutting path. That's exactly the case with this part here. In this case, since we can't use a boring ring, consider using a plug of material to hold the jaws in position. Before profiling the jaws, we will take a small cut on the inside diameter of the jaws equal to the plug diameter. We will use the adjustable boring ring again to hold the jaws while making this initial bore. We check the plug diameter and enter it into the IPS diameter to cut field. Boring the jaws this way will hold the plug in the best possible manner. One of the important benefits of using the plug is that you can exert full desired clamping force on the jaws. You can eliminate the need to add a taper to the jaws by matching high jaw cutting pressure to high workpiece cutting pressure. With the bore for our plug complete, we clamp it at the center of the jaws, leaving adequate clearance for the cutting path. We apply the clamping force to the plug in the same direction and pressure that will be used on the workpiece, which in this case is 250 psi. Before cutting these jaws, Andrew notes that unlike our previous part, the finish on this material is very rough. Despite this variation, in our case, we will still cut the pocket to hold the raw stock at the nominal stock diameter. Realizing that in some cases, we will be holding at the 6 edges of the jaws, and other times at the 3 centers. Now, we will be making 2-step jaws for this part, and with our program set to cut both pockets to the nominal size, we are ready to cut our jaws. Two-step jaws are a good alternative to cutting 2 different jaw sets. When part geometry is favorable, the larger pocket holds the uncut raw stock, while the smaller pocket holds the half-finished part for the second operation. With these 2-step jaws cut and grooved as before, we are ready to start making parts. Thank you for watching. Be sure to check out our other soft jaw videos where we cover the essentials of ID gripping and other topics including adding tapers and recutting your jaws.